Welcome back. I'm now going to do a slightly harder two-dimensional projectile motion problem. So let's start by drawing the ground. So this is the ground, and I'm going to leave a lot of space so that we can do other things with this chalkboard. Let's draw the ground like this. And let's say I have something, let's say, I don't know, let's say it's a slingshot. And it's angled up at, let me think of a good angle. It has an angle of, so the initial slingshot's angle, so just, the angle at which it's pointed is, this angle is 30 degrees. 30 degrees. And I want to hit a target that, I don't know, let me just make up a number. Let me say it is 100 meters away. I want to know, and I'm on Earth, so I'm dealing with gravity. I want to know how fast does the slingshot's velocity in this direction, in the 30-degree direction. I want to know what this initial velocity needs to be for me to hit this target exactly. So let's see if we can figure this out. So we know, well, we don't know the initial velocity, but let's pretend like we do, and maybe we can break it up into its horizontal and vertical components. So let's just do that right here, since we already have the vector drawn out. Actually, no, let me do it in the corner up here. So the first thing we want to do is break it up into its horizontal and vertical components. So this is our initial vector, and it's vi. That's our initial. We could just call it, oh, let me call it vi, initial velocity. It's initial velocity in this direction, in the direction of, the 30 degrees to the ground. And we want to break that up into its horizontal and vertical velocities. Or we could say it's along the x-axis or the y-axis. Oh, whoops. We could say, I want to be neat this time, because I think it helps your concentration, maybe. I don't know. So everything with horizontal will be purple, and everything with vertical or along the y-axis. Oh, whoops. I just said that and then I changed my convention. Oh, I'm malfunctioning. That's that. That's that. And we're ready to rock and roll. And this angle right here is 30 degrees. So instead of saying along the vertical direction, let me change this along the y-axis. So you can think of kind of in the traditional coordinate axes. So what is the component of the velocity along the y-axis? Well, we learned from the last presentation, you could just use standard trigonometry, right? Opposite the vy, v sub y. This is v sub y right here, this line right here. Actually, I'm using the wrong color. V sub y over the hypotenuse, v sub I, is equal to sine of 30 degrees. Or we could say v sub y is equal to the initial velocity times sine of 30 degrees. And what's sine of 30 degrees? Sine, if you remember your 30, 60, 90 triangles, you maybe remember this by now. But sine of 30 degrees, worst case, use a table or a calculator. But hopefully you know what the sine of 30 degrees is. It's 1/2. So we know that my vertical velocity, last time I called it v sub v, this time I'm going to call it v sub y, because it's kind of going along the y-axis. My vertical velocity is equal to 1/2 times my initial velocity. Boy, that looks like an L. I don't know why. Did I actually say that in L a little while ago? Anyway, that's v sub I, right? So it equals 1/2 v sub I, right? And, oh, where was I? Oh, yeah, my brain really is doing something else right now. Anyway, and this 1/2 is just the sine of 30 degrees. And what is my horizontal velocity? Let's get all the trigonometry out of the way. Well, my horizontal velocity, doing it the exact same way here. Let's call that v sub x. V sub x is equal to v sub I, my initial velocity, times the cosine of 30 degrees. Cosine of 30 degrees. And if you remember your 30, 60, 90 triangles, you'll remember cosine of 30 degrees is square root of 3 over 2. So v sub x is equal to v sub I times the square root of 3 all of that over 2. So how do we figure out how far? Let's say we didn't know we had to get to 100 meters. How do we figure out how far this projectile, whatever is coming out of my slingshot, is going to go? Well, we figure out how long it's going to stay in the air. And then once we figure out how long it stays in the air, we can just multiply it times our horizontal velocity, and it'll tell us how far it goes. So how long is this thing stay in the air? Well, for that we use our vertical velocity, or v sub y, right? So we know that change in velocity. Let me switch back to that other color. We know that change in velocity is equal to acceleration times time. And what I want to do is figure out how long does it take for this object to kind of get to its maximum height. So it's decelerating from this vertical velocity, v sub y, to 0. And how long is it going to take to do that? Well, let's see. The change in velocity is 0 minus v sub y, which is this. So it's 0 minus v sub y, which is my initial vertical velocity, the y-axis. So it's 1/2 v sub I. I just wrote this instead of this. And that equals acceleration. We're going to say minus 10 meters per second squared times time. I'm not writing the units for the sake of efficiency. And so let's see, if I divide, so this doesn't matter, right? The 0 doesn't matter. This and this, if I multiply both sides by -1. And then if I divide both sides by 10, I get t. T is equal to 1/20th v sub I, or v sub I over 20. So is this the total time of the travel of the object? Well, no. This is the time that it takes the object to kind of start at a very fast initial vertical velocity. So it's, initially it starts at this velocity, and then it keeps decelerating until at some point along its curve, like here, where its vertical velocity is 0. And then it starts decelerating or accelerating downwards and comes here. So just remember, let me draw the curve actually, because I think that might make it. So the object is going to take a path like this. Whoops. Something like this, right? At this point, the object has its full vertical velocity and its full horizontal velocity. And at every point, as we get higher and higher, gravity slows down its vertical velocity. It slows down v sub y. It slows down its vertical velocity, but the horizontal velocity stays the same. And at this point, the peak point, its vertical velocity, how fast is it moving upwards, is 0. And then its vertical velocity turns negative. And it starts accelerating in the negative direction, or decelerating in the positive direction, depending how you want to view it. So this time tells us literally how long did it take to go from this initial vertical velocity to 0. So that's how long does it take to get to this point. So the total time that I'm traveling is going to be twice this, right? So let's say total time in the air. Let me call it time in the air. That could be a good. So time in the air. We could call this time up, right? And then time up plus time down, and they're equal to each other, is equal to time in the air. Time in the air is going to be equal to 2 times time up. And that equals 2 times this, which is equal to 1/10 v sub I, or vi, over 10. So we know now how long this object will stay in the air as a function of its initial velocity in this 30-degree direction. Now we have to just figure out how far is this thing going to travel. And I think I'm running out of time, so I'm going to continue this in the next